Let's start with number 9 in 2.7. Now, learning this may not seem all that exciting. And you're right, it's not all that exciting. And you might feel like it's lame because you're not going to use it ever again in your life, and you're right. Unless you're a math teacher or a rational function grapher or you become a graphing calculator, you're not going to use this much. But just to get on my soapbox for just a moment, whatever you do in your life, you're going to be commended for being someone who can think critically and rationally. And that's we use that a lot in what we're doing here. We decide what this graph is going to have to look like because we've determined its truth by this expression here. You're going to be able to tell somebody, hey, this is definitely what the graph has to look like if this is the expression you're using. As you put in different values of x, this is what the graph is going to have to look like. And you learn to apply that to other parts of your life. Wherever you are, you can look at a situation and say, look, if this is what you want, if these are the parameters you're working in, and this is your desired outcome, this is what you're going to have to do. You could do that for yourself, you could do that for others, and this really does enforce that line of thinking. Whether you believe it or not, it doesn't change the fact that that's true. So hopefully that's a little bit of motivation to keep going with this and not say it's stupid and I don't want to do this anymore. So with that, let's go ahead and get started. So the things that we've learned to do are to find zeros of polynomials and find vertical asymptotes and horizontal asymptotes of rational functions. And we're going to take that, put it all together, and make a graph. So first let's look at the vertical asymptotes. Remember that a vertical asymptote will only happen if the denominator is equal to 0. You'll remember that another possibility is having a hole in your graph. First we're going to treat it like it's a vertical asymptote. So a vertical asymptote could happen here at x minus 2. And remember, the only way that this isn't a vertical asymptote is if the numerator has a common factor of x plus 2, or the exact same statement would be to say that negative 2 is a 0 of the numerator as well. At the same time that this is a 0, so is this. But that's not the case. So this is a vertical asymptote at negative 2. Okay. And now we'll look at horizontal asymptotes. Well, it's just a matter of the degree of the numerator versus the degree of the denominator. The degree of the denominator is greater than the degree of the numerator, so we can see the denominator is going to become very large, while the numerator in this case only is 1 ever. So 1 divided by very large is very small, very close to 0. So your horizontal asymptote is going to be right here at 0. Okay, and this horizontal asymptote, remember, it guides us as we get really far out to the left and to the right on this graph. So, let's get started on graphing this. Really, the only things we need to know now are maybe there's some x-intercepts, and then what's it doing at this vertical asymptote? Because we know it's doing at the horizontal asymptote. It's going to approach it. Some of the questions are: does it approach it from the bottom? Does it approach it from the top? Does the asymptote make the graph go this way, or does it make it go this way on either side? Okay, so for the first thing, let's see if there's any x-intercepts. It's possible. Because keep in mind, you might be thinking, well, there's a horizontal asymptote, so it's not going to cross the horizontal asymptote. But remember, that's only for the ends, right? If it were to help, you could just kind of not draw a horizontal asymptote in this region, and only on the ends does the horizontal asymptote tell you what the graph's going to do, okay? And even for some functions, some trigonometric functions and perhaps others, your graph will actually cross the horizontal asymptote forever and ever and ever, but it'll get smaller and smaller and eventually look like it's just at your horizontal asymptote. Anyway, we're going to see if there's any x-intercepts. That would happen if this whole thing were equal to 0, but that can never happen because in order for this to be equal to 0, then the numerator would have to be 0. If the denominator is 0, then you have a vertical asymptote. You have an undefined function. So only the numerator being 0 will cause this to be 0, and that's not possible because the numerator is always 1. We could multiply both sides by x plus 2, and 1 would have to be equal to 0, which is impossible, so there's no x-intercepts. Okay, so let's look what's happening here on this side, and what's happening here on this side of the vertical asymptote. Because now that there's no x-intercepts, we know that it's got to, if it came up from from positive infinity, it would have to come in, not cross the x-intercept, or not cross the x-axis, and just kind of slide right along the horizontal asymptote. Okay, so let's see where it's coming from. Let's put in numbers, whether you use your graphing calculator or your mind. I prefer my mind if I have a choice. So on the left, we're going to find numbers that are slightly smaller, and by smaller I mean more negative, like negative 2.01. So let's think about negative 2.01 plus 1. That's negative 0.01. That's 1 over a negative, so that's going to be a negative. And we know the nature of a vertical asymptote is to send the function off to some infinity, either positive or negative. So in this case, it's going to go negative because it's going to be 1 divided by negative 0.01, or 1 divided by 0.000001. And that's going to go to the negative infinity. Now, just on the other side, you're going to find numbers like negative 1.99999. So negative 1.99999 plus 2 is going to be something like 0.000001. So 1 divided by 0.000001 is going to be some really big positive number. So we're going to have the function going off to positive infinity. And since there are no x-intercepts, we know that this graph is going to have to do something like this. Okay, simple example. Now let's look at number 19. Just 10 problems down the road. All right, vertical asymptotes, horizontal asymptotes, x-intercepts, maybe a y-intercept, plotting some points. We're going to figure this out. Okay, so vertical asymptotes. That will happen where the denominator is equal to 0 unless this numerator has a common factor with the denominator, which we can see that it doesn't. These are both completely factored into their linear factorization, and there's no common factors. There's no factor of x up here. There's no factor of x minus 4 up here. There's no factor of x plus 1 down here, so no common factors, no cancellation. So x could be equal to 0, x could be equal to 4. At these places, since there's no common factors in the numerator, we will find vertical asymptotes. Now let's use a different color on this one. Going to positive 4. All right, so we've got a couple pieces of information there. Now let's look at horizontal asymptote. Degree of the numerator versus the degree of the denominator. First degree, second degree. Second degree gets much bigger. Second degree is going to mean that this much bigger number is going to be divided into this relatively small number, which means we're going to approach 0. Okay. Let's do x-intercepts. Remember, x-intercepts are only going to happen where the numerator is equal to 0 unless the denominator has common factors, which we already said that it doesn't. So only when x is equal to negative 1 will this happen. So we've got an x-intercept at negative 1. All right, and now we just need to plot some points. Now where we want to plot points, basically think of it this way. There are Interesting things, interesting places on a graph like this: x-intercepts and vertical asymptotes. So in between any combination of those features, between two asymptotes, between an asymptote and an x-intercept, between two x-intercepts, we're going to plot some points, right? And so the way we're going to do that quickly is use our graphing calculators. Now we could do this without our graphing calculators. For example, and this is the reason why. I want to know if it's going to, maybe this function comes up like this, crosses the x-intercept, comes up a little bit, and then we know it has to approach the horizontal asymptote, so maybe it does that. Or maybe it goes this way. And so we need to know some points. So if I plot a point somewhere in here, say at -2, then I'll know some significant information about this graph. So if I put -2 in here, -2 plus 1 is -1. We've got -4 up there. -2 minus 4, that's -6 times -2. That's going to be a positive 12. So a 4, or -4, over a positive 12 would be a -1/3. So that's going to be somewhere right there. Okay. And really, if you think about it, that's all the information we actually need. We know that as we approach vertical asymptote, it either needs to go positive infinity or negative infinity. And we know that it crosses the x-axis here, so we know that it's down here on this side, and it's up here on this side. It's got to go to positive infinity. If it went to negative infinity, there'd be another x-intercept here. That's what I'm talking about thinking critically. That's the cool thing about math, is it makes you do that. So this is going to come, and I don't know exactly where it starts to turn around, but that's not the important part. The important part is that we just show that it does turn around and start to approach that horizontal asymptote. Okay, and here, what happens? Well, I know, for one thing, that it does not go like this, from negative infinity from there up to positive infinity, and neither does it go that way, because what? There would be an x-intercept in here, and there's not. So it either comes like this or like this. Okay, so it's just a matter of really just finding a point somewhere in here. Why don't we just put a 1 in there? 4 times 2, that's going to be 8. That's -3 times 1, -3. So a positive 8 over a, what did we say? -3, positive 1 over a -3. That's going to be a -8/3. So here's 1 and 2 and 3, almost 3 at positive 1, -8/3. So what we know here is that it's got to come up through that point, turn around, and go back this way, because I can't cross the x-axis because there's no x-intercepts there. Okay. And on the other side, this doesn't cross the x-axis. We know it's got to come like this or like this. So we got to decide, is it up here or is it down here? Put in a 5. 5 plus 1, that's 6. 6 times 4, that's 24. And you put a 5 here. 5 minus 4 is 1. 1 times 5 is 5. So that's going to be positive, right? And it's going to be positive, what do we say? 5, 6, 24 over 5. So somewhere near 5-ish, a little less than 5. Right there. So it's going to come down from positive infinity, cross through that point, and go off in that direction. All right, so if you were to graph this function, as I'm doing now, that's exactly what it looks like. Exactly what it looks like. Maybe not exactly, but really close. All right. That's the same. So why don't we go to something like 43. 43 is super interesting. All right, I'm going to stop writing in red. It's so violent. F of x is equal to 2x squared plus 1 over x. This is the kind of function I just love. It's so crafty. All right, so first let's look at vertical asymptotes. We love to look at vertical asymptotes. We could look at them all day. They're mystifying, like the aurora borealis. Okay, vertical asymptotes. Clearly going to happen at x equals 0. Right? No common factor of x up here. Okay, pretty simple. Now, horizontal asymptotes. Will there be any horizontal asymptotes? There's only going to be a horizontal asymptote if either the degree of the numerator and denominator are the same, or the denominator has a greater degree. But this now, the numerator has a greater degree. It's degree 2 versus a degree 1. So this numerator is going to get much larger in comparison to the denominator, the degree of the denominator. So we're basically, this guy's going to take over, and as x goes to positive infinity, depending on whether this function becomes positive or negative, which it'll be positive, it'll shoot off to positive infinity, and as we go to negative, it'll shoot off to negative infinity. But how it does that is very interesting. Okay, this graph does not have a horizontal asymptote, but it has something called a slant asymptote. Okay, so in order to do that, let's write this not this way, but using the division algorithm. We know that if we divide these two, we can write it as, let's see, not the division algorithm. We just know that we can write this as some other polynomial plus a little remainder. That's what we know. And since this is a linear factor, we're just going to go ahead and use synthetic division. And let's see. Yeah, so we're going to put a 0 out here as we do our work. And we put a 2 and a 0 for x and a 1. And so bring down the 2, and that's a 0, a 0. Multiply that by a 0, and that's a 1. So we have 2x squared plus 1. Let's just say that's equal to this new polynomial, which is 2x, no constant, plus 1 over x. Plus 1 over x. And that, that 1 right there is the remainder, and that 1 is kind of what we said at the beginning when we started dividing these things. It's like that little piece that still needs to be divided by x, and so that's what we're showing that's happening. So the interesting thing about this is that look at what this function looks like as the numbers get very large. This number, or this part of it, is if you let me just bring something up here. Think about what's happening as the numbers get very large. And think about what's happening to that remainder. I'm going to take this down here. That remainder is just its own little rational function. And the degree of the numerator is smaller than the degree of the denominator, so this thing just kind of goes away. Oh, I'm glad that happened. Should bring it up here. It just kind of goes away. And so all that's left is this guy right here. Let me just... It's not all that there is, but it's like that. 1 plus x doesn't matter. It really doesn't matter. It doesn't give much influence anymore. It's like nothing's there. It's 1 divided by this huge number, so it's gone, essentially. So this function will act like 2x. Way out on the right side and way out on the left side, it'll act like 2x. Right? So it will act like the line 2x with a y-intercept of 0 and a slope of 2 up 2 and over 1 and down 2 and over 1 and right? And let's draw this dotted line. Right? So that, I mean, that's pretty cool, I think. It's pretty interesting because on positive and negative infinity, or as we approach positive and negative infinity, this guy just doesn't even matter. Put in 1,000,000, 1 over 1,000,000, it's like nothing's there. But put a 1,000,000 over here, you have 2,000,000, right? And way out on the extremes, you're just not adding on very much to this 2x, so it acts just like 2x, almost exactly like 2x, until you get in towards the middle where this 1 over x is not so small anymore. It has more influence. So that's where you get this slant asymptote, because this thing acts like a line, the line 2x, except for when you get towards the center, so to speak, of the graph. So I guess I can't make that sound more interesting than I have. If it sounded interesting, then cool. If not, then let's just keep going. Now let's look at possible x-intercepts. So that's going to happen when the numerator is equal to 0. X squared plus 1 equals 0. So 2x squared equals -1, and x squared equals -1/2. And of course, you couldn't square something and get a negative number, so there are no x-intercepts. Right? There's no x-intercepts because there's no real solutions to this equation. So we know that it doesn't approach the slant asymptote and cross the x-axis and go up like that. Okay, that's interesting. So let's just find out what does happen. Let's plot some points in this region, right, to the left of this vertical asymptote and to the right of this vertical asymptote, like 1 and -1. So if we put in a 1, it's like maybe a little easier actually to do it here. Put in a 1, you get 2 plus 1, 3. That's a 3. So at 1, you get a 1, 2, 3. So let's see the possibilities. Maybe it starts at negative infinity at this asymptote, comes up here, goes through this through this point, and then approaches the slant asymptote from there. That couldn't happen because there would be an x-intercept there, and there's no x-intercepts. So it must be, the only other option on this side is that it comes from positive infinity, crosses this point, and then approaches this line that we talked about earlier. It approaches this line right here, 2x, and as it goes out further and further and further, if you were to take a spaceship and fly, millions of light years in this direction, probably actually just a couple of miles would do it, but you would find yourself unable to distinguish this graph, this blue thing, from this dotted line 2x, because this would be so insignificant that it would not be influencing the difference between this graph, this rational function, and the graph of the line 2x. Unless you had some really sophisticated instrumentation, you wouldn't be able to do it. Okay, so let's look on this side. Either this guy comes in from here and then approaches the line, but that couldn't happen because there's an x-intercept. So actually we know that it has to come from here, go through some point there, and then go this direction. Right? And we could do that by putting -1 in there. That'd be -2 minus 1. Let's see, yeah, minus 1/2. No, minus 1, because we're putting in a -1 there. So -2 minus 1 would be -3. So -1, -3. We find a point. Okay? See, those are the things that I like about, well, math in general. You just find things out that have to be true, and no one can tell you otherwise. Actually, the real fun is when somebody tells you that you're maybe wrong, and then you talk about it and figure it out. Okay. But you'd have to major in math to run into that. Here we go. We're going to find vertical asymptotes here. That would be where the denominator is equal to 0. But x squared will never be negative 4 and have real solutions for x, so no vertical asymptotes. So now let's look at horizontal asymptotes. Do you see the degree of the numerator is the same as the degree of the denominator, which means that as we go out to negative and positive infinity, these two values are going to basically balance each other out. And the value of that will be pretty much, the same thing over the same thing, which will be, as we get out to positive and negative infinity, it'll be pretty much a positive 1. Okay. Now, let's look at maybe a y-intercept. Since we don't have a vertical asymptote, we're kind of hurting for some information. So let's look at vertical asymptote, or a y-intercept. We put a 0 in here and in here. We get negative 1 over positive 4, so negative 1/4. Right? Now let's look at x-intercepts. That'll happen where x squared minus 1, the numerator, equals 0. So x squared equals 1. X equals plus or minus 1. So at plus and minus 1, we will find some x-intercepts. And this is, again, the cool thing about math to me is that you know that it has to be down here and it has to come up through this x-intercept. And you know that it has to then approach this horizontal asymptote. Wow, that looks good. Okay, you know that has to happen. You've done your math correctly. You determine where x and y intercepts are, what the horizontal asymptote has to be, that there are no vertical asymptotes. You know exactly what has to happen. And the graph would have to look like this, or very close to this, with maybe some slight differences. And that's the cool thing. So, there you go. No one can tell you different. 48, so let's look at number 50. Alright, number 50 is... Alright. This will be the last one. Okay, again, looking at vertical asymptotes. They're only going to happen if the denominator is equal to 0, unless, so let's say unless, the numerator also has a factor of x minus 2. So in order to find out, just really quickly, if the numerator has a factor of x minus 2, then I should be able to do this synthetic division and come out with a remainder of 0. Let's just try it real quick. 4, negative 1, and negative 2. That is not a 0, so x minus 2 is not a factor of the denominator or the numerator, and so there is what that tells us that it is a vertical asymptote and not a whole. Okay, so there is a vertical asymptote at 2, right? Because x would have to be equal to 2. All right. Next, let's look at a horizontal asymptote. Well, it's not going to have a horizontal asymptote, right? Because the degree of the denominator is less than the degree of the numerator, which means this guy's going to take over and we're going to go to the infinities, right? And if you'll notice again, the degree is off by 1. So if I were to divide this into this, I would wind up reducing this by 1 degree, and I would have a degree 1 polynomial. So actually, we had just done that. If I divide x minus 2 into 2x squared minus 5x plus 5, this is a 2, 4, negative 1, negative 2, and a 3. Okay, so this turns out to be the same as 2x minus 1 plus 3 over x minus 2. And we had talked about how as we go off to positive and negative infinity, this becomes less and less influential. It changes the value of this, right? Less and less. It adds less and less to this. So this is what we call a slant asymptote, with a y-intercept of negative 1 and a slope of 2. There we go. We know that this rational function is going to look a lot like this line when we get out to its outskirts, to negative infinity and positive infinity. So, pretty cool, pretty interesting. All right, now we have to find out maybe some x-intercepts. So let's do some work in blue. Some x-intercepts. That's only going to happen when this guy is equal to 0, right? And I can try and factor this real quick. We know we need a 2x and an x and 2 negative numbers because they're going to multiply to make a positive and add together to make a negative. My only options are 5 and 1, so this does not seem like it's going to work out. Right? If I put a 5 here and a 1 here, then I'm going to get 5x minus negative 5x minus 2x, that's negative 7x. And if I put a 5 here and a 1 here, I'll get a negative 10x and a negative 1x, and that'll be negative 11x. So it's not factorable. It's irreducible over the rationals. So whenever that happens, we like to use the quadratic formula. Over 2a, so that'll be 4. (25 minus 40). Okay, so we can see already, even before I wrote this, that this is going to be negative. Take the square root of a negative. It's not real, so we don't have any real zeros. We don't have any x-intercepts. All right. Which tells me that it's definitely not going to come up from here and then cross the x-intercept, or cross the x-axis at all, and come back down. And it definitely can't come from positive infinity and go that way. So I know already, since there's no x-intercepts, it's got to do something like that. On this side, one possibility is that it comes from here and then goes off that direction, but it can't do that because there's no x-intercepts. So I know it's got to do something like this. So I could be done. I know that it's got to look something like this. And since obviously we're not plotting every point and being super accurate, we know that the graph has to look very similar to this. So we could be done with that. All right. So I hope that was helpful for you, and just let me know if you have any questions.